Welcome to Session 11, Compound Probability and Counting. Multi-stage chance problems become manageable when every branch and outcome is defined before calculating. 10 practical examples cover independent and dependent events, mutually exclusive and overlapping events, complements, tree reasoning, and the fundamental counting principle. Translate n into multiplication or into a carefully checked union and at least 1 into 1 minus none. Update probabilities whenever an outcome is removed. Example 1. 2 fair coins are flipped. Find the probability of 2 heads. The comparison places both cases on the same scale. Plan. List the equally likely ordered outcomes or multiply independent probabilities. Step 1. The sample space is 8H, HT, TH, TT, TT. Step 2. Only HH has 2 heads. Step 3. Compute one favorable outcome divided by 4 total outcomes equals 1/4. Step 4. Equivalently, 1/2, 1/2 equals 1/4. Quick check. The 4 outcomes are equally likely and exactly 1 is favorable. This matters in real life because multi-stage chance models appear in genetics, inspections, and repeated decisions. Example 2. Customer independently has a 0.8 chance of paying on time in each of 2 months. Find the probability of on-time payment in both months. The probability scale locates the result between impossible and certain. Plan. For independent and events, multiply the probabilities. Step 1. Let A be on-time payment in month 1 and B in month 2. Step 2. Independence means PA and B equals PAA, PB. Step 3. Compute 0.8 times 0.8 equals 0.64. Step 4. The probability of on-time payment in both months is 64%. Quick check. The probability of both events is smaller than the probability of either single event. This matters in real life because businesses use repeated payment probabilities when estimating cash flow. Example 3. A bag contains 3 red and 2 blue marbles. 2 are drawn without replacement. Find the probability both are red. The comparison places both cases on the same scale. Plan. Update the favorable count and total after the first draw. Step 1. The first red probability is 3/5. Step 2. After 1 red is removed, 2 red remain among 4 marbles. Step 3. Multiply. 3/5, 2/4 equals 6/20. Step 4. Simplify to 3/10 or 30%. Quick check. The second probability must be 2/4, not 3/5, because the bag changed. This matters in real life because without replacement models describe sampling items for inspection or selection. Example 4. A fair die is rolled. Find the probability of rolling a 1 or a 2. The probability scale locates the result between impossible and certain. Plan. The outcomes cannot happen together on one roll, so add their probabilities. Step 1. P1 equals 1/6 and P2 equals 1/6. Step 2. The events are mutually exclusive on one roll. Step 3. Add 1/6 plus 1/6 equals 2/6. Step 4. Simplify to 1/3. Quick check. Counting favorable faces directly also gives 2 out of 6. This matters in real life because mutually exclusive categories are common in one-choice survey and routing outcomes. Example 5. From a standard deck, what is the probability of drawing a heart or a king? Account for overlap. The overlapping circles show outcomes that belong to both events. Plan. Add the 2 event probabilities. Then subtract the king of hearts counted twice. Step 1. There are 13 hearts and 4 kings. Step 2. The king of hearts belongs to both events, so the simple sum double counts 1 card. Step 3. Favorable cards equals 13 plus 4 1 equals 16. Step 4. The probability is 16/52 equals 4/13. Quick check. Listing the union should contain the 13 hearts plus the 3 non-heart kings, totaling 16. This matters in real life because overlap correction is used when customers or records can belong to multiple categories. Example 6. A uniform shop offers 4 shirts and 3 pairs of pants. How many outfits contain 1 shirt and 1 pair of pants? The key quantities are organized before the arithmetic begins. Plan. Use the fundamental counting principle for sequential choices. Step 1. There are 4 choices for the shirt. Step 2. For each shirt, there are 3 choices for pants. Step 3. Multiply 4 times 3 equals 12. Step 4. There are 12 possible outfits. Quick check. A 4x3 table would contain 12 shirt-pants cells. This matters in real life because retailers count combinations when planning product variants and catalog displays. Example 7. 5 finalists are available for president and vice president. How many ordered assignments are possible? The key quantities are organized before the arithmetic begins. Plan. Choose the first role, then the second role from the remaining people. Step 1. There are 5 choices for president. Step 2. After choosing a president, 4 people remain for vice president. Step 3. Multiply 5 times 4 equals 20. Step 4. There are 20 ordered role assignments. Quick check. Order matters because swapping the 2 people changes their roles. This matters in real life because organizations use ordered counting when positions or task assignments differ. Example 8. A restaurant meal has 2 soup choices, 3 main course choices, and 2 dessert choices. Find the total complete meals. The key quantities are organized before the arithmetic begins. Plan. Multiply the number of options at every independent selection stage. Step 1. Start with 2 soup choices. Step 2. For each soup, there are 3 mains, giving 2 times 3 equals 6 partial meals. Step 3. Each partial meal can use 2 desserts. Step 4. Compute 6 times 2 equals 12 complete meals. Quick check. A 3-level tree would end in 12 branches. This matters in real life because menus and product configurators rely on staged counting. Example 9. A weather model gives rain probability 0.3 on Saturday and 0.4 on Sunday, treated as independent. Find the probability it rains on neither day. The comparison places both cases on the same scale. Plan. Use complements for each day, then multiply the independent no-rain probabilities. Step 1. P no rain Saturday equals 0.3 equals 0.7. Step 2. P no rain Sunday equals 0.4 equals 0.6. Step 3. Multiply 0.7 times 0.6 equals 0.42. Step 4. The probability of no rain on either day is 42%. Quick check. Both no-rain events occurring should be less likely than either one alone. This matters in real life because weekend event planners combine multi-day weather risks. Example 10. A machine has a 0.1 defect probability per independent item. Find the probability that at least one of 2 items is defective. The probability scale locates the result between impossible and certain. Plan. Use 1 minus the probability of no defects. Step 1. The probability one item is not defective is 0.1 equals 0.9. Step 2. The probability neither of 2 items is defective is 0.9 times 0.9 equals 0.81. Step 3. Compute 0.81 equals 0.19. Step 4. The probability of at least one defect is 19%. Quick check. The result includes exactly 1 defect and 2 defects without double counting cases. This matters in real life because quality control teams use complement methods to estimate batch risk. Session 11 recap. Multiply along branches for and events, add valid alternatives for or events, and subtract overlap when an outcome belongs to both events. Without replacement creates dependence. The counting principle multiplies the choices at successive stages. At least one is often easiest through the complement of none. Quick check. 3 shirts and 4 pairs of pants can form how many shirt and pants outfits? Multiply 3 choices by 4 choices. There are 12 outfits.